Welcome to Nitoria. It's lovely to have you here tonight. Wherever you are right now, however the day has folded itself up behind you, I'm glad you found your way to this quiet corner of the night. Maybe you're lying in bed with the lamp still glowing somewhere off to the side. Maybe you're on a couch with a blanket pulled up, or on a long train ride watching the dark slide past the window, or somewhere I couldn't begin to guess. So let me ask, the way I always do before we drift off into anything strange and far away, where in the world are you listening from tonight? What time is it in your corner of the dark? It's a small thing, I know, but I like to imagine all of us scattered across the planet, in different beds and different cities, all settling in together for the same slow journey. And if you find that you enjoy these slow journeys, if you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already here, already part of Nitoria, who come back night after night, thank you. Truly, you're the reason the lamp stays on. Now tonight, we're going somewhere a little unusual. We're going to the edge of a black hole, not falling in, not really, just drifting up close to the rim, the boundary, the strange, invisible line that physicists call the event horizon. And we're going to do it slowly, one quiet fact at a time, 100 of them if we get that far, though I rather suspect many of you will be fast asleep long before we reach the end. And that's perfectly all right. That's the whole idea. The black hole will still be here when you wake. The facts aren't going anywhere. If you drift off in the middle of a sentence about the bending of light, that's not a failure. That's the plan working exactly as it should. So you don't need to concentrate. You don't need to remember any of this. You don't need to understand every single thing I say. And honestly, some of it is the kind of thing that nobody fully understands, not even the people who've spent their whole lives studying it. I'll try gently to make all of it make a little bit of sense as we go. But there's no test in the morning. There's no need to grasp every number. Just let the words wash over you like a slow tide and let yourself sink. I will say one thing the same way I always do. I'll try my best not to make any of this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something strange and true about the universe. A fair trade, I think. So, let's begin, shall we? Softly. I want to start with something almost impossible to picture, and yet, in its way, very simple. Imagine you could float perfectly safe, perfectly calm, at exactly the right distance from a black hole. Not too close, not too far. A very particular distance which we'll come back to later in the night. And imagine you turned your head and looked off to the side, not at the black hole itself, but along a line that just grazes past it, out into the dark. You would see the back of your own head. Sit with that for a moment slowly, the way you'd sit with a dream just before it dissolves. The light leaving the back of your head would travel outward, and instead of streaming off into space the way light always does, it would feel the pull of the black hole and bend. It would curve. It would swing all the way around the black hole in a great slow arc, a full circle, and come right back to you and land in your eyes. You'd be looking at yourself from behind. Not a reflection in a mirror. No. The actual light, the actual photons that left you, looping the long way around the darkness and returning home. There's a place near a black hole where light can do this, where gravity bends the path of light so completely that light travels in a circle. We'll meet that place properly later and learn its name. But I wanted to open the door with it because it tells you something about where we're going tonight. The edge of a black hole is a place where the most basic things you trust, light traveling in straight lines, time moving forward, up being different from down, all of it quietly comes loose, gently, without drama. The rules just start to relax, the way your shoulders are relaxing now, the way your breathing is starting to slow. Here's another image to drift on. Imagine you watched from a safe distance as something fell toward a black hole, a probe, a stone, a glowing lantern, anything. As it fell, you'd expect it to speed up, the way things always speed up when they fall, and to vanish over the edge in an instant. But that's not what you'd see at all. Instead, the falling thing would seem to slow down as it neared the edge, slower and slower and slower still. Its light would grow dimmer and it would shift toward red, the way the sound of a passing train drops in pitch as it goes by. Only this is light, sliding down toward the deep red and then toward darkness. And the falling thing would never quite arrive. It would seem to hang there, just above the edge, frozen, fading, getting redder and fainter and more still, but never crossing. For the rest of time, from where you sit, it would simply hover at the rim, an image growing ever dimmer, never quite gone. A frozen figure at the edge of the dark, suspended, going nowhere, forever. And here is the strange and beautiful part. The thing that fell, if it could speak, would tell you a completely different story. From its own point of view, nothing odd happened at all. Its own clock ticked along perfectly normally. It fell, and it reached the edge in a perfectly ordinary amount of time, and it crossed over without any fanfare, without any wall, without any moment that felt like an ending. Two observers. Two completely different accounts of the very same event. And the truly remarkable thing, the thing that took physicists a long time to make peace with, is that both of them are right. Neither one is mistaken. The universe simply allows two different true stories to exist at once, depending on where you're standing. We'll come back to that, to how it can possibly be that something freezes at the edge forever, and yet also falls right through. There's an answer, a lovely one, and we'll reach it slowly much later in the night. For now, just let the image rest with you. The frozen figure at the edge and the same figure falling peacefully through. Both true. No rush. So let's slow down even further and ask the most basic question of all. What is this edge, really? What is the thing we keep calling the rim, the boundary, the event horizon? And the first surprising answer is this. There's nothing there, nothing at all. The event horizon is not a surface. It's not a wall. It's not a shell or a skin or a membrane, not a thin film stretched across space that you could reach out and press your hand against. There is no there in the sense of stuff. If you were falling toward a black hole and you crossed the event horizon, there would be no barrier to push through, no moment of contact, no sensation of passing a threshold. You would feel absolutely nothing to mark the spot. No bump, no shimmer, no line painted on the dark. The event horizon is a mathematical boundary in space-time. That's all it is. It's the name we give to a particular place, defined not by any object sitting there, but by a property of that place. And the property is this. The event horizon is the last place from which light can still escape. Step 1, hair's breadth outside it, and light, given enough of a push in the right direction, can still climb away and reach the wider universe. Step 1, hair's breadth inside it, and no light, no matter which way it's aimed, can ever get out again. The horizon is just the dividing line between those two regions. The line between the part of space that can still send a message to the rest of us and the part that can't. So when we say the edge of a black hole, we're not talking about an object. We're talking about a place where a certain rule changes. It's a bit like the line on a map that marks where one country ends and another begins. You can stand right on that line, but there's nothing physically there. No glowing fence, no wall built across the landscape. Just an idea, a boundary we agree on. Except the boundary at the edge of a black hole isn't about which side of a river you're on. It's about whether or not you can ever come back. And because there's nothing physically there, here's a thought that surprises almost everyone. For a big enough black hole, you could cross the event horizon completely unharmed. Completely. You'd feel nothing. Now you've probably heard somewhere along the way frightening stories about black holes tearing things apart, stretching them out like long, thin threads. And that does happen, and we'll talk about it gently much later when it won't disturb your sleep. But it's not the whole story, and it's certainly not the story at the edge of a truly enormous black hole. There are black holes out there that weigh millions of times as much as our sun. Supermassive black holes, we call them, the giants that sit at the hearts of galaxies. And around a giant like that, the pull of gravity changes so gradually, so smoothly, from your head to your feet, that there's almost no difference between them. Nothing tugs you apart. Nothing warns you. You could drift across the event horizon of one of these vast, ancient things in perfect calm, in perfect silence, and not feel a single thing to tell you that you just crossed the most important line in the universe, the line beyond which there is no return. The edge of a black hole, the very thing our stories make so violent and so terrible, can in truth be utterly serene. A quiet, invisible threshold, crossed in the dark, without a sound. So if the edge isn't a wall and isn't an object, and you can't feel it, then what decides exactly where it is? What sets the rim? The answer comes back to that idea of escape. You may have heard the phrase escape velocity. It's just the speed you'd need to fling something away from a world so that it never falls back. Throw a ball up into the air and it comes down because you didn't throw it fast enough. Throw it faster and it goes higher before it returns. Throw it fast enough and it never returns at all. It just keeps going out into space. That threshold speed, the speed that lets you finally escape for good, is the escape velocity. On Earth, it's about 11 kilometers every second, which is fast, far faster than any ball you could ever throw, but a rocket can manage it. Now imagine an object so dense, with gravity so strong, that the escape velocity climbs higher and higher, faster than a rocket, faster than anything we could build, and then imagine it climbing further still until the speed you'd need to escape reaches the speed of light itself. The speed of light, the fastest speed there is, the cosmic limit that nothing can cross. That's the edge. The event horizon is precisely the place where the escape velocity reaches the speed of light. And since nothing at all, can travel faster than light, it means nothing can escape from inside that boundary, not a rocket, not a signal, not even light itself. The edge is simply the place where the threshold for getting out becomes impossible to meet. Below it, you'd need to go faster than light to leave, and you can't. So you don't. So nothing does. That's all the edge really is, the place where leaving stops being allowed by the deepest law in physics. And here's a lovely thing about that boundary. We can say exactly how big it is with a single number, and that number depends on only one thing: the mass, how much stuff went into making the black hole. The size of the event horizon is called the Schwarzschild radius, and we'll meet the man whose name that is in just a little while. The rule for it is beautifully simple: about 3 kilometers of radius for every sun's worth of mass. So if you took our sun, our own ordinary star, and somehow squeezed it down, crushed it until it became a black hole, its event horizon would be only about 6 kilometers across. 6 kilometers. That's small enough to sit comfortably inside a single city. You could walk across it in an afternoon if it weren't, of course, a black hole. The entire sun, all of that fire and light, the thing that warms every living place we know, its edge of no return, would be smaller than the town you grew up in. And because the rule is so simple, just a steady 3 kilometers of radius for every sun of mass, it scales up in the gentlest, most predictable way. A black hole 10 times heavier has an edge 10 times wider. A black hole 1,000 times heavier, 1,000 times wider. A black hole, 1,000,000,000 times the mass of the Sun, has an event horizon 1,000,000,000 times broader than that little 6-kilometer one. There's a wonderful tidiness to it. The edge grows exactly in step with the mass, no surprises, no sudden jumps, and there's no upper limit, not in principle. Whatever the mass, however vast, there's an edge to match it, growing ever wider, ever calmer, the bigger the black hole becomes, which leads us to something that genuinely surprises most people, and it's a soft, strange fact to drift on. We tend to think edge of a black hole and immediately imagine something unbearably dense at the boundary, something crushing, something packed tight. And deep down at the very center, yes, the story does get strange, and we'll tiptoe toward that much later. But at the edge itself, at the horizon of one of these giants, the density can be astonishingly low. Here's why. The edge grows in step with the mass, but the volume inside the edge grows much, much faster. So as a black hole gets bigger, all that mass ends up spread across an enormous ballooning region. And if you simply take the mass and divide it by the volume inside the horizon, the way you'd work out the density of anything, you find something almost comical. For a supermassive black hole, the average density inside its edge can be lower than the density of water. You could, in a manner of speaking, float in it, and for the very largest of the giants, the average density inside the event horizon drops lower than the density of air. Thinner than the air in the room around you right now, the most fearsome object in the universe, and on average, inside its boundary, it's emptier than a quiet breath. Edge of a black hole does not have to mean crushing density at the rim. For the great ones, it means something closer to a vast, soft, hollow, dark. Now, we keep using this name, the Schwarzschild radius, so let me tell you slowly where it comes from, because the story of how we first understood the edge is itself a quiet, rather moving thing. The year is 1916. The First World War is grinding across Europe, and a German physicist named Karl Schwarzschild is serving in the army on the Russian front in the cold and the mud and the noise of that terrible war. Just months earlier, Albert Einstein had published his great theory, general relativity, his new way of understanding gravity not as a force pulling things together, but as the bending and curving of space and time itself. Mass tells space how to curve. Curved space tells things how to move. It was a beautiful idea, and a difficult one, wrapped up in equations that even Einstein found hard to solve. And there, at the front, amid the artillery and the misery of war, Schwarzschild sat down and solved them. He worked out the very first exact solution to Einstein's equations, the precise mathematics describing the space around a single round mass. And buried inside his solution was something peculiar, a particular radius, a particular distance from the center where the maths seemed to do something strange and dramatic. That distance is the one we now call the Schwarzschild radius. It marked, though no one quite understood it yet, the edge, the boundary of no return. The event horizon, glimpsed for the first time, not through a telescope, but through pen and paper in a soldier's hand in the middle of a war. Schwarzschild sent his work to Einstein, who was astonished that anyone had solved his equations so quickly, let alone someone in the field. And then, the following year, in 1917, Karl Schwarzschild died. He fell ill at the front and did not recover. He never knew what his radius truly was. He never saw a black hole, never knew that the strange distance he'd found in the maths marked the rim of one of the most extraordinary objects in all of nature. He died long, long before anyone believed such things could really exist. He gave us the edge and then he was gone, and it would take the rest of the century for the world to understand what he'd handed it. For a long time after that, nobody even had a good name for these objects. The equations described them. The strange edge was right there in the maths, that distance where time and light seemed to do impossible things. but the things themselves felt too outlandish to be real, and the name we use now, black hole, didn't arrive until much later. It was popularized only around 1967 by the American physicist John Wheeler, who had a gift for finding the perfect words for difficult ideas. Black hole. Two simple words that somehow caught the whole imagination of the world, and we've never let go of them since. But before that, before Wheeler's name took hold, these objects had a different name, and it's my favorite of the two because it's so gentle and because it captures exactly the thing we've been drifting on tonight. They were called frozen stars.
Frozen stars, isn't that lovely? And do you see why? Think back to the falling figure from earlier, the one that seemed to slow and redden and hang at the edge forever, never quite crossing. From the point of view of someone watching from far away. Now imagine that, but for a whole star. When a great star runs out of fuel and collapses under its own weight, falling inward to form a black hole, the outer view is exactly that strange, frozen one.
From far away, the collapsing star doesn't simply vanish. It seems to slow as it shrinks toward its own forming edge. Its surface appears to freeze in place, its light fading and reddening, the collapse never quite finishing. The star seems to hang there, suspended at the moment of its own ending, frozen in the sky. A frozen star, a star caught in the act of disappearing, held still at the edge of itself, its last light slowly draining away to red and then to dark. That's what the outside universe sees, not a sudden ending, but an endless, fading pause. The star froze at its edge in our sky, and there, in a sense, it remains. So we have these two names, one calm and one stark, for the very same thing. Frozen star for the way it looks from the outside, slowed and suspended and fading at its rim. And black hole for what it becomes what it is, the deep, dark pit from which nothing returns. Both names are true. Both describe the edge we're exploring tonight. And both, in their own way, are gentle reminders that the edge of a black hole is far stranger and far quieter than the fearsome thing of our stories. Let your breathing settle into that for a moment. The soldier solving the equations in the cold of a distant war and dying before he knew what he'd found. The star, frozen forever at the edge of itself, its light slowly dimming in the sky. The invisible boundary with nothing there to touch, no wall, no surface, just a line where escape becomes impossible and light can no longer climb away. The vast, soft, hollow giants, emptier inside than the air you're breathing now. And somewhere out near the rim of one of them in the dark, the back of your own head lit by light that traveled the long way round. We've only just begun to map the edge. There's so much more waiting in the quiet ahead. We haven't yet talked about why exactly. Time seems to stop there. The deep reason underneath it. The strange way that the inward direction stops being a place you could choose to go and becomes something more like tomorrow, something you can't avoid no matter how you turn. We haven't yet stood at that particular distance where light bends into a perfect circle and learned its proper name, or seen how the darkness in the famous photographs is bigger than the black hole itself. We haven't felt the way a spinning black hole drags the very fabric of space around with it, like water turning slowly down a drain so that nothing nearby can hold still. But all of that is still ahead of us in the soft dark, waiting patiently. There's no hurry to reach any of it. So for now, just rest here at the edge we've drawn so far. The invisible line, the frozen star, the quiet, serene threshold that you could cross without ever feeling it pass. And let's drift slowly toward the strangest thing of all about that edge. The thing that happens not to space, but to time. Before we drift into time, though, let's stay a moment longer with the edge itself, because there's a quiet little mystery in what it actually is, and it's gentler than you might expect. When you imagine the boundary of a black hole, it's easy to picture something solid, a dark shell, a wall hanging in space, the way a cliff face hangs at the end of a field, but there's nothing there, truly nothing. No surface, no membrane, no skin stretched across the dark. If you reached out a hand toward the event horizon, there would be no moment where your fingers met something firm. The horizon is not made of matter at all. It's a place defined by a rule, not by a thing. It's simply the last line in space from which light can still get away. One step further in, and even light, the fastest thing there is, can't climb back out. That's all the edge is. A boundary drawn by what light can and cannot do. And here's the part that surprises almost everyone. If the black hole is large enough, you could cross that line and feel absolutely nothing, no jolt, no tug, no sense at all that you'd just passed the most important threshold in the universe. For one of the truly enormous black holes, the supermassive ones that sit at the centers of galaxies, weighing millions of times more than the Sun, the pull at the edge is gentle, spread out. There's no violent stretching at the boundary, no warning shudder. You could be drifting along, half asleep yourself, and slip across the event horizon in perfect calm, the way you might cross from one dark room into another without noticing the doorway. The edge can be utterly serene. So if there's nothing there, what actually marks the line? It comes down to a single idea, and it's one you already half know: escape velocity. To leave the Earth, a rocket has to reach a certain speed, about 11 kilometers a second, or gravity simply pulls it back down. Every object in space has a speed like that, a speed you'd need to break free of its pull. The more massive the object, the higher that speed climbs. And a black hole is so dense, its gravity so concentrated, that as you fall toward it, the escape speed rises and rises until at one particular distance, it reaches the speed of light itself. That distance is the edge. Right there, you would need to travel at light speed just to get away, and go any closer, and you'd need to go faster than light, which nothing in the universe can do. So nothing leaves, not a rocket, not a signal, not the faintest glimmer of light. The horizon is just the place where that threshold quietly tips over the line. This distance even has a proper name and a beautifully simple rule behind it. It's called the Schwarzschild radius. And the lovely thing is that it depends on only one number, the mass, nothing else. Not what the black hole is made of, not how it formed, not its history, just how much it weighs. The rule is about 3 kilometers of radius for every sun's worth of mass. So if you could somehow take our own sun and crush it down until it became a black hole, its edge, its event horizon, would be only about 6 kilometers across. Small enough to sit comfortably inside a city, tucked between the streets with darkness where its center would be. All of that brightness and warmth and weight folded down into a sphere of shadow you could walk around the rim of in an afternoon. And because the size depends only on the mass, it scales perfectly with no ceiling at all, make the black hole 1,000 times heavier, and its edge is 1,000 times wider, 1,000,000,000 times heavier, 1,000,000,000 times wider. There's no upper limit written anywhere in the equations. The horizons just keep growing, gently, in step with the mass, all the way up to the monsters, wider than whole solar systems. But here's something that turns the usual picture on its head. We tend to imagine the edge of a black hole as the densest, most crushing place imaginable. And for the small ones, that's true. But for the giants, it isn't, because the radius grows in step with the mass, but the volume inside that radius grows much, much faster. So the bigger the black hole, the more thinly its mass is spread across the space inside its edge. For a supermassive black hole, the average density inside the horizon is actually lower than water. And for the very largest known, it's lower than the density of air. Sit with that for just a moment, as you're lying there breathing. The edge of one of these colossal things, the boundary past which nothing can ever return, encloses something less dense, on average, than the quiet air around your own bed tonight. The terror isn't in the crush at the edge. The edge is mostly emptiness, wrapped around emptiness. Now, all of this, the radius, the rule, the whole geometry of the boundary was worked out astonishingly early and under conditions you wouldn't believe. The man who first solved the equations for the edge was named Karl Schwarzschild, and he did it in 1916, only months after Einstein had published his great theory of gravity, general relativity. That alone would be remarkable, but Schwarzschild wasn't sitting in some peaceful university study with a warm lamp and a pot of tea. He was a soldier serving on the Russian front in the middle of the First World War. Out there, amid the cold and the noise and the danger of it all, he took Einstein's brand new equations and found the exact shape of the space around a black hole, the precise size of its horizon. He sent his solution back to Einstein, who was, by all accounts, astonished that anyone had found such a clean answer so quickly. And then, the following year, in 1917, Schwarzschild died of an illness he'd caught at the front. He passed away long before anyone took black holes seriously as real things that could actually exist out in the universe. He glimpsed the geometry of the edge, gave us the very radius that still bears his name, and then was gone, decades before the rest of us caught up to what he'd seen. And the strange thing is, even the name we use now is younger than you'd think. For a long time, nobody called them black holes at all. The term we all know, black hole, was only really made popular around 1967 by a physicist named John Wheeler, who had a gift for finding the perfect words for difficult ideas. Before that, these objects went by a different name, one that's quietly beautiful in its own right. People called them frozen stars. Frozen stars. Sit with that phrase for a moment in the dark. It came from exactly the thing we touched on at the very start. The way a collapsing star, watched from far away, seems to slow down as it forms its horizon. From a safe distance, you'd see the star falling inward, and then, as its surface neared the edge it was creating, you'd see that collapse appear to slow and almost stop. The light reddening, dimming, the whole thing seeming to freeze in place at the boundary, hanging there, never quite finishing its fall. So that's what they were named for, not for the dark, but for that stillness. A star caught forever in the act of vanishing, frozen at the edge of itself in our sky. And that name, frozen star, points us straight toward the deepest strangeness of all, the one we keep circling back toward. Because for the star to look frozen there to us, while the star itself, in its own experience, falls all the way through without ever slowing, something has to be happening to time. Something has to be bending and stretching and splitting apart, so that two perfectly honest observers can watch the very same event and tell two completely different stories of it. And both of them are right. That is exactly the mystery we're going to follow. Deeper now, like a thread you've been holding and are only just beginning to pull. So let's talk about what time actually does at the edge. You remember from a moment ago that inside the horizon, the inward direction becomes your future, not a direction you might choose to travel, the way you might walk south or climb a staircase, but the future. Unavoidable, like Tuesday. That is not a poetic way of putting it. It is the literal geometry of the situation. Outside a black hole, space-time is arranged in the ordinary way you live with every day, though you almost never think about it. You move forward in time whether you like it or not. That's simply the nature of having a dimension called time. But in space, you can go left or right, toward the window or away from it. You have freedom in space and you are carried in time. At the event horizon, those two things quietly exchange their roles. Once you cross that boundary, the spatial direction pointing toward the center of the black hole changes its character. It becomes time-like. meaning it points toward your future, the way tomorrow does. The center is not a place you could turn around and walk away from, any more than you can walk away from next week. It sits ahead of you in time, not in space. And this is not a force holding you there, not gravity yanking at you the way an ordinary pull would. It is simply the shape of the universe at that location, the geometry. The map itself has been redrawn. Outside, time flows forward and space is open in all directions. Inside, time flows toward the center, and space, in that particular direction, is closed. The edge is the place where that exchange occurs. One side of the line, ordinary space-time. The other side, a space-time where a particular compass direction is no longer a direction at all, but a moment. Physicists sometimes describe it this way. Space and time swap roles at the horizon. Outside, you are free in space and carried in time. Inside, you are free in time in the sense of having some remaining amount of it, but carried in space toward the center, as surely as you are carried toward any future moment. This is what makes the event horizon so unlike anything you've encountered before. It is not a surface of crushing force, it is a surface of rewritten geometry. A place where the universe quietly revises its own rules, not loudly, not with any physical sensation you could point to, but absolutely and permanently. And this brings us back to the frozen star and to one of the most beautiful and disorienting facts in all of physics. Imagine you are watching from a safe distance a friend falling toward a black hole. They are in a capsule, falling freely, and you are watching through a telescope. What do you see? You see them approaching. You see the capsule getting closer to the edge, and then, gradually, you see something strange. Their motion seems to slow, not because anything is physically stopping them, but because the light carrying information about them is taking longer and longer to climb out to you as they descend deeper into the gravitational well. Each photon they emit has to work harder to escape, and the time between successive photons reaching you grows longer and longer. Their clock, as you watch it, runs slower. A second for them becomes 2 seconds for you, then 10, then 1,000. Their image reddens because each wave of light is stretched on its long journey out to you, shifted toward the lower frequency end of the spectrum. They dim because the photons thin out, arriving less and less often. And then something genuinely remarkable. They approach the horizon and their clock appears to stop altogether. Their image hangs there, reddened to near invisibility, frozen at the boundary, never quite crossing. In principle, you would never see them cross. The last light they emit just before the horizon would take an infinite amount of your time to reach you. They appear in your sky to freeze there for the rest of the universe's life. This is exactly why those early physicists chose the name frozen star. The star itself appeared to stop at the horizon of its own making and hang there, caught in the moment of its crossing for all eternity. But now shift your perspective. You are no longer the distant observer, you are the friend in the capsule. From your point of view, nothing unusual happens as you approach the edge. Your watch ticks normally. Your thoughts continue at their usual pace. You feel no sudden jolt, no shudder, no warning that you have arrived at anything significant, particularly not if the black hole is very large and the tidal forces at the horizon are gentle. You cross. You keep falling. You may not even notice the precise moment you passed, the point of no return. To you, a finite amount of time passes. The crossing happens. It is real. It is complete. To the person watching from far away, the crossing never happens. You are frozen at the edge forever. Both stories are correct. Not one of them is an illusion, not exactly. They are two different descriptions of the same event, as experienced from two different positions in curved space-time. The universe permits both simultaneously without contradiction, because simultaneity itself is not absolute. There is no cosmic master clock that arbitrates whose version is the real one. This is one of those facts that is worth sitting with in the quiet of the dark before sleep. Not a simplified version of physics, not a rough approximation, the actual geometry. Two people, one event, two complete and irreconcilable stories, both fully true. And there is a corollary to this that is perhaps even stranger. Since the distant observer never sees anyone cross, in a strict sense they never see anything actually pass through the horizon. Every object that has ever fallen toward a black hole has, as far as a distant observer is concerned, simply been accumulating at the edge, slowing and reddening, smearing against the boundary, not gone, smeared, frozen, present, in an infinitely attenuated way at the surface. Their light never quite stops reaching you. It just stretches out, each successive signal taking longer to arrive than the last, so that in principle you are still receiving the final photon that left them a moment before crossing, a photon that is by now so stretched and so faint and so delayed that no instrument in any practical universe could detect it. But it is there, in theory, still arriving, still carrying the last image of a figure at the edge. Now the light from someone falling in does something precise and remarkable as it climbs back out to you. It is redshifted, the wave is stretched, the frequency drops, visible light becomes infrared, then radio waves, then wavelengths so long they carry almost no energy at all. This is gravitational redshift, and it grows without limit as the source approaches the horizon. The horizon is, in the language of the mathematics, a surface of infinite redshift for outside observers. Any signal trying to escape from right at the edge would need to be stretched by an infinite factor to reach you. And something stretched by an infinite factor has, in any real sense, faded to nothing. But here is the flip side that is easy to miss. For the person falling in, the light coming down toward them from outside is not redshifted, it is blue-shifted. The universe outside is sending its light downward, and that light is compressed on its way in, shifted toward higher frequencies, toward the violet and the ultraviolet and beyond. In a sense, the infaller receives the universe's light at a higher pitch. The cosmos outside beats faster and brighter against the window of the falling capsule than it does for anyone hovering safely above. This connects to something we'll return to more carefully in a later part of the night, the full strangeness of what the infalling observer sees in the sky. But there is a gentler version of it already implied here, which is simply this. Near the horizon, time runs differently depending on where you are. A clock close to the edge ticks slowly relative to one far away. The closer you are, the slower your time relative to the universe outside. This is gravitational time dilation, and it is real in a very everyday sense. The GPS satellites in orbit around Earth have to correct for it constantly. Time runs very slightly faster for them than for clocks on the ground, because they sit higher in Earth's gravity well, and without corrections, this tiny difference would cause your navigation to drift by kilometers over the course of a day. Near the edge of a black hole, the effect is not tiny, it is enormous. Consider what this means. If you could somehow hover just outside the horizon, perhaps just a few meters above the place where the escape velocity equals the speed of light, your time would run almost infinitely slowly compared to the universe outside. An hour of your time might correspond to an age of the universe, or longer, outside. You would be aging at almost no rate compared to the cosmos you came from. This gives rise to one of the quieter, remarkable possibilities in the mathematics. Hover near the horizon for what feels to you like a short time, and return. The universe outside has aged enormously. You could, in principle, use the edge of a black hole as a one-way trip into the deep future. Not a machine exactly, not a door you could step through repeatedly, but a consequence of sitting in a place where time runs slowly and then returning to where it runs fast. In the language of science fiction, this is time travel. In the language of general relativity, it is simply what space-time does when it is sharply curved. and the edge of a black hole is about as sharply curved as anything gets. But here is the trouble. Hovering near the horizon is not easy. It is, in fact, very nearly impossible, and becomes exactly impossible right at the edge itself. To remain stationary near a black hole, you must fire engines. Gravity is pulling you in, so you must push outward against it. The closer you are to the horizon, the stronger the pull, and so the harder you must push. This is not unusual. You feel something like it whenever you climb a steep hill, but at the edge of a black hole, the required force does not just become very large, it grows without limit as you approach the horizon. There is no stable ledge just outside the event horizon where you could stand and rest. Standing there, in the sense of remaining stationary relative to the distant stars, requires you to fire engines at a thrust that grows toward infinity as you approach. Right at the edge, the thrust required to hover would be infinite. Infinite thrust does not exist. The horizon has no stationary surface, no perch you could occupy. You either fall or you burn unlimited fuel. And the edge itself is, by definition, the place where the unlimited becomes the literally impossible because no finite force in the universe can hold you there. This is connected to something strange about light at the edge. Imagine you fire a flashlight outward just above the horizon. The beam heads away from the center, climbing against the gravitational field. As it rises, it loses energy to the climb, its frequency dropping, redshifting. Near the horizon, the light must lose almost all its energy just to escape to any significant height. By the time it reaches a distant observer, the light has been stretched enormously, its frequency lowered, its energy reduced. The closer to the edge the flashlight was when you fired it, the more energy the light loses in the climb. Right at the horizon, the light that was aimed outward has, in a certain sense, just enough energy to escape, and just barely. If you fire from just inside, the light aimed outward does not escape at all. It is bent back inward by the geometry of space-time. You could say the horizon is where light grows tired, where the climb is too steep and the signal barely makes it out at all. The edge is where the universe runs out of voice. And while we are here, in the strangeness of time and space near the edge, there is one more thing worth settling into before we move on. Outside a black hole, the ordinary intuition of a shared now, of two distant observers agreeing on what is happening at the same moment, is already not strictly accurate. This was already true in special relativity before gravity was even part of the picture. Two people moving at different velocities do not agree on which events are simultaneous. That was strange enough when Einstein first proposed it. Near the edge of a black hole, the effect is much more dramatic. Two people at different distances from the horizon or moving through the curved space-time in different ways can disagree on simultaneity so severely that events one person considers already past, the other has not yet experienced. The very notion of now dissolves at the edge. There is no global present tense near a black hole. There is only each observer's local experience, each telling a different story of the same curved universe, neither story the master copy. We are creatures who take now for granted. This moment, the present. We assume that right now, somewhere far away, specific things are happening. A particular rain is falling, a particular light is burning. But space-time near the event horizon is a quiet but complete demonstration that this assumption is not a feature of the universe. It is a convenience, a comfortable simplification that holds well enough in the gentle curvatures of everyday life, but dissolves completely when the curvature grows sharp. At the edge, now is not a thing that can be agreed upon. These facts, the stopping of time for outside observers, the frozen crossing, the infinite redshift, the near-infinite thrust required to hover, the tired light, the dissolving now, are all different facets of the same underlying geometry. They are all consequences of the event horizon being the place where the future points inward, where space and time have traded their roles, where the curvature of space-time has reached its boundary condition. They are not separate mysteries. They are one mystery, seen from different angles. Let the weight of that settle. You do not need to hold all of it at once. It is enough to feel the shape of it. That the edge of a black hole is not a place in the ordinary sense. It is a rearrangement of the universe's most basic categories. And now we move to a different kind of strangeness at the edge, one that is geometric in a more visual, picturable way, one you can close your eyes and almost see. Above the event horizon at 1.5 times the Schwarzschild radius, there is a place called the photon sphere. The Schwarzschild radius, as we touched on earlier, is the radius of the horizon itself, roughly 3 kilometers per solar mass, with the horizon sitting there as the inner boundary. The photon sphere sits outside it, but not by much. At 1.5 times that distance from the center, something happens to light that has no everyday parallel whatsoever. Gravity at that distance is strong enough to bend light into a complete circle. Not a gentle curve, not a slight arc, a circle, a closed orbit. A beam of light traveling in the right direction at that precise distance will simply go around and around the black hole, curving continuously, never arriving anywhere, never escaping, bending in an orbit just as a planet bends in an orbit. Except the planet is a photon and the orbit closes on itself. Light can orbit a black hole. Take a moment to let that be concrete rather than abstract. A photon, which moves at the speed of light because it is light, arrives at this sphere traveling in just the right direction, and instead of continuing outward to the stars or falling inward to the center, it enters a circular path. It goes around, it comes back to where it started, it goes around again, a beam of light in orbit. Now here is the consequence of that, the one that is hard to stop thinking about once you've heard it. If you were somehow hovering at the photon sphere and you looked sideways along the direction the orbiting light travels, you would see your own face, the back of your head, your own ears. Light leaving the back of your head would travel around the black hole along that circular path and arrive at your eyes from the other direction. You would see yourself not as a reflection in a mirror where the image is reversed, but as the back of your own head, as if you were looking at yourself from behind. This is not a metaphor or a thought experiment designed to be evocative. It is a direct consequence of the geometry of the photon sphere. If you were there, and light from your head traveled tangentially along the orbit and completed the circle, it would arrive at your eyes. The light is real, the path is real, the seeing would, in principle, be real, but the photon sphere does not offer a stable home. The orbits there are unstable. This is crucial. Think of a ball perched on the very peak of a hill, balanced at the top. It could, in the ideal frictionless mathematics, sit there forever, precisely balanced. But the slightest nudge, the gentlest breath, the tiniest perturbation sends it rolling one way or the other, down the hill or down the far slope. The balance at the peak is real, but it is a balance that cannot last. The photon sphere is exactly like that peak, but for light. A photon traveling at exactly the right angle at exactly that distance is in orbit, but nudge it inward, even slightly, and it spirals toward the center, crossing the horizon. Nudge it outward even slightly, and it escapes to infinity. The orbit is balanced on a knife's edge, a mathematically precise but physically impermanent equilibrium. In any real physical situation, orbits at the photon sphere will not persist for long. This instability is part of what gives black holes their distinctive appearance when we photograph them. The dark region in those famous images is not the horizon itself. The horizon is smaller than it looks. What we see as the shadow of the black hole, that dark disk surrounded by glowing light, is actually larger than the horizon by a significant margin, roughly 2.5 times the Schwarzschild diameter. The The reason is the photon sphere, background light coming from behind the black hole, from distant stars and glowing gas, is bent by gravity as it passes. Some of it curves just enough to miss the black hole and continue outward, some bends sharply and falls in. But light that passes near the photon sphere is bent most dramatically, curving toward extreme angles, producing a magnified shadow, a dark region in our sky that is noticeably larger than the horizon alone would make it. The photon sphere stretches the apparent darkness, making the black hole look bigger than its edge alone would suggest. Around the edge of that shadow, there is a bright ring, the photon ring. This is where things become even more beautiful. The photon ring is not just one ring, it is a composite made of light that has looped around the black hole various numbers of times before escaping toward us. Some of the light in that ring looped once around the hole before heading our way. Some looped twice, some 3 times. Each additional loop corresponds to a slightly different position in the ring, nested concentrically, packed ever more tightly toward the ring's edge. In the idealized mathematics, this nesting continues without end. There are, in principle, infinitely many subrings, each made of light that circled one additional time compared to the last, each sitting fractionally closer to the shadow's boundary. They pile up like echoes, each fainter and thinner than the one before, until they become too small for any real instrument to distinguish. The resolution we have today, even with the extraordinary Earth-spanning telescope that captured the first images, can resolve only the outermost of these rings. The rest are there, nested inside, waiting for instruments of the future. This means the bright ring you see in those images is not just light from around the black hole, it is a compressed archive of the entire illuminated universe as seen from that direction, each subring containing light that circumnavigated the black hole one more time, each one a faint repetition of the view, folded over and over into an ever tighter halo at the edge of the darkness. And there is one more layer of strangeness at the photon sphere, one that emerges when the black hole is not just sitting still but spinning. A spinning black hole does not have a single photon sphere. It has a range of photon orbits, different for different kinds of light. Light that travels in the same direction as the black hole's spin, prograde light, finds the orbital radius is smaller. It can orbit closer in, pulled forward by the spin. Light that travels against the spin, retrograde light, has to orbit farther out. The 2 sets of orbits bracket a range of unstable circular paths that straddles the photon sphere of a non-spinning hole. This asymmetry has a direct observational consequence. The shadow of a spinning black hole is not a perfect circle. It is slightly flattened or shifted on one side because the frame dragging that moves space itself around the hole affects how light bends going with the spin versus against it. The silhouette of the edge is not symmetric. It leans very slightly in the direction of the spin. When astronomers studied the image of M87 and of Sagittarius A, they were looking, among other things, for exactly this kind of shape, for the subtle asymmetries that reveal how fast the black hole is turning. The edge, even photographed from 55 million light-years away, carries the signature of its own rotation, written in the bending of the light around it. So the photon sphere is not merely a curiosity of the geometry, it is the reason the black hole casts the shadow it does. It is where the infinitely nested bright ring is born, and it is where, in the most literal sense the mathematics permits, you could look sideways and see yourself looking back. Now let's rest here for a moment, in this layer of the night, before we go deeper. We have moved through the most basic disorientation of the edge, the fact that it is not a surface, that it is a one-way membrane in time, that inside it the inward direction is your future, and you cannot refuse it any more than you can refuse tomorrow. We have seen how time appears to stop for the outside observer, how every falling thing freezes and reddens at the boundary and is, in principle, never seen to cross. How the infaller notices nothing and crosses in finite time. How these two stories are both fully true simultaneously. How the light from someone falling in is stretched to infinite wavelengths on its way out. How the horizon is a surface of infinite redshift. How light grows tired climbing away from the edge. We have seen how the clock near the horizon runs slowly and how hovering there could, in principle, deliver you into the far future of the universe. How hovering requires nearly infinite thrust, and how right at the edge there is no such thing as standing still. How the very idea of now dissolves in the curved space-time near the boundary. And then we moved outward slightly to the photon sphere, where gravity bends light into closed circles, where orbits exist but are balanced on a knife's edge of instability, where you could see your own face returning to you across the arc of the universe, where the shadow of the black hole is born and the nested rings of multiply-looped light are packed into a halo of infinite depth. These are the first layers of the edge, the ones built from the geometry of the boundary itself, the strange properties of a place where the future has changed direction. There is more ahead, deeper and stranger still. Frame dragging and the ergosphere, where space itself is swept around in a current. The innermost stable orbit, where matter can no longer circle safely and begins its final fall. The view from inside the fall itself, and the slow, cold, almost impossibly faint glow of Hawking radiation, the edge that barely glows, the edge that quietly and over unimaginable time disappears. But there is no hurry, the night is long, and these ideas have been here since long before you arrived at them, and they will be here in the morning, waiting if you want to find them again. If you are still awake, perhaps you're resting with the image of light in a circle, orbiting a dark center, the photon sphere, as a halo of impossible geometry above the edge. Perhaps you're turning over the quiet strangeness of the time stopping, the way a person falling in appears to freeze and redden and thin out into near nothingness at the boundary, while they themselves feel nothing cross freely and continue into a future that has changed its direction. It is a strange universe that permits this. Strange and very large and very old. And you are here, lying in it, made of the same physics, carrying in every atom the same laws that curve space-time near a black hole, only operating in a much gentler regime. You are subject to gravitational time dilation too, very slightly. The floor of the room you're in is at a lower gravitational potential than your ceiling, and a clock on the floor ticks, in principle, infinitesimally slower than one above it. The difference is too small to matter in any practical way, but it is the same effect, the same geometry. Extended, extrapolated, taken to its extreme, it becomes the frozen star, the infinite redshift, the time that stops at the edge. The universe does not make exceptions, it simply scales. Let the breath slow now. The edge is still there, impossibly far away, curving space-time around itself, bending light into rings, stopping clocks, swapping space and time at its boundary, silent and dark and patient. We'll move deeper into it in a little while. The ergosphere is next, the place where space itself is in motion, where the spinning hole has set the universe rotating around it, where you cannot hold still even if you try. And then the innermost orbit, and the infalling view, and the slow, cold light of the evaporating edge. But for now, simply rest with what you've learned. And here is where the strangeness of the edge deepens in a different way. Not through time, this time, through motion. A black hole that spins does something that a non-spinning one does not. It does not merely sit in space and curve it, it drags space around with it, like a spoon stirring honey, except the spoon is a collapsing star of millions or billions of solar masses, and the honey is space-time itself, and the stirring never stops. This is called frame dragging. More precisely, it is called the Lense-Thirring effect, after Josef Lense and Hans Thirring, who worked out its mathematics in 1918, 2 years after Schwarzschild found the horizon equation in his wartime letter. They predicted it from general relativity before there was any hope of measuring it. The idea was this: a rotating mass does not simply pull other things toward it. It pulls the very fabric of space-time around with it, twisting and sweeping the geometry of space in the direction of its spin. Think of it this way: imagine you are floating in a river, and the water is perfectly still. You can face any direction you choose. You can hold yourself in place. The water is just a medium you sit in. Now imagine the river begins to rotate, slowly at first, as if someone far below is stirring it in a great slow circle. Gradually, you find that holding a fixed position requires effort. You drift. You have to compensate. The water itself has acquired a direction, and that direction pushes you. Near a spinning black hole, this is what happens to the geometry of space. It rotates, not the matter in the space and everything in it is pushed to rotate along. Far from the black hole, this effect is small, extremely small. Even Earth, spinning on its axis once a day, drags space-time around it by a tiny, measurable amount. Scientists measured it with an experiment called Gravity Probe B, a spacecraft launched in 2004, carrying 4 gyroscopes so perfect they had spherical surfaces accurate to 40 atoms. Over a year of orbiting, those gyroscopes tilted by a precise, tiny angle because Earth's rotation dragged the space they were traveling through. The Lagios satellites, heavy metal spheres placed in orbit and tracked by laser with extraordinary precision, confirmed the same effect independently. Earth's frame dragging is real. It is also fantastically gentle, so small that it barely matters for anything except the most careful measurements. Near a black hole, nothing about it is gentle. As you approach a spinning black hole, frame dragging intensifies. Space near the edge is not sitting still waiting for you. It is being swept around in the direction of the hole's rotation, faster and faster the closer you get, and there comes a point, outside the event horizon itself, where the sweeping becomes so severe that no force in the universe can keep you stationary. You cannot hover, you cannot point yourself against the spin. Even light going as fast as anything can go cannot move upstream against the dragging of space in certain directions. You are forced to rotate with the black hole whether you want to or not. This region is called the ergosphere. The ergosphere is not the horizon. The ergosphere sits outside the horizon, surrounding it like a thick outer layer. Outside the ergosphere, you can still fight the current, still hold yourself in place if you have powerful enough engines, still orient yourself however you choose. Inside the ergosphere, you cannot remain stationary relative to the distant stars. The rotation of space has become mandatory. You are carried around whether you consent to it or not. But here is the crucial thing: you can still leave. The ergosphere is a place of forced motion, not of no escape. It lies outside the point of no return. If you enter the ergosphere and then fire your engines or use the right trajectory, you can still climb back out to safety. It is not a trap. It is more like a very strong current you can, with enough effort, swim out of. The horizon is the drain itself. The ergosphere is the whirlpool around it. The shape of the ergosphere is worth picturing because it is not a simple sphere. It is flattened, somewhat like a pumpkin, bulging more at the equator and pinching in near the poles of the spinning hole. At the poles, the ergosphere surface actually meets the event horizon itself. At the equator, it extends furthest out. The faster the black hole spins, the more pronounced this bulge becomes. The more the ergosphere extends outward at the equator, the more dramatic the difference between the polar regions and the middle. A slowly spinning hole has a modest, nearly round ergosphere. A maximally spinning hole, one rotating as fast as physics allows, has an ergosphere that reaches far out at the equator, giving the whole structure a distinctive lopsided oblate geometry. Now, the ergosphere's forced motion sounds purely threatening, but it turns out you can exploit it. In 1969, the mathematician and physicist Roger Penrose described a remarkable mechanism. If you enter the ergosphere and split an object into two pieces, carefully arranged so that one piece falls inward with negative energy relative to a distant observer, while the other piece escapes outward, the escaping piece carries away more energy than the original object brought in. You have, in effect, stolen energy from the black hole, not from the infalling matter, but from the black hole's own rotation. The hole pays for your gain by spinning slightly more slowly. This became known as the Penrose process. Roger Penrose, he would go on in 2020 to share the Nobel Prize in Physics for proving that black holes must contain singularities, a proof that convinced much of the physics community that these objects were not mathematical curiosities, but real. But the process named for him in 1969 was itself a different kind of discovery, a demonstration that the black hole's rotation is a reservoir of energy, and that the ergosphere is the place where that reservoir is accessible. How much energy is there? The answer is startling. For a maximally spinning black hole, the energy stored in its rotation represents up to 29% of its total mass energy. That is enormous. Mass energy, in Einstein's accounting, is vast, and 29% of it is sitting in the spin, in principle extractable, if you could engineer the right trajectories in the ergosphere. A sufficiently advanced civilization, in principle, could use a spinning black hole's ergosphere as a power source. Drop things in with the right geometry, collect the returning fragments with more energy than you invested, repeat. The black hole gradually slows, its ergosphere shrinks, but for an enormous spinning hole with enormous angular momentum, this could continue for a very long time. Nature itself may already be doing something like this. Not through falling objects exactly, but through magnetic fields. When a spinning black hole is surrounded by an accretion disk, magnetic fields thread through the disk and through the ergosphere. The spinning of space in the ergosphere tangles and wins those field lines. Energy can be extracted electromagnetically from the black hole's rotation and flung outward along the magnetic field lines in two powerful jets, one shooting out from each pole of the black hole's spin axis. These jets can be extraordinarily powerful. Some stretch for millions of light years, some carry enough energy to heat and reshape entire galaxy clusters. The mechanism behind this is called the Blandford-Znajek mechanism, after Roger Blandford and Roman Znajek, who described it in 1977. It is one of the leading explanations for how quasars shine as brightly as they do. A quasar, in many cases, may be a spinning black hole in a particularly well-fed stage, with the ergosphere and frame dragging actively converting rotational energy into the most powerful continuous light source in the observable universe. The brightest objects we can see across cosmic distances may be running in large part on frame dragging, on the ergosphere, on the geometry of space being dragged in circles around the edge of a black hole. Let that rest for a moment. There is another boundary worth knowing, closer in than the ergosphere. It is called the Innermost Stable Circular Orbit. Abbreviated, the ISCO. The idea is this: objects can orbit a black hole just as planets orbit a star. Far enough out, a circular orbit is stable. Small perturbations do not cause the orbit to decay. The object can circle indefinitely or close enough to it. But as you move inward, closer to the black hole, something changes. The orbits become less and less stable, and eventually you reach a point inside which no stable circular orbit exists at all. Inside that point, any orbit decays, The object spirals inward and falls past the horizon. The ISCO is the last stable orbit, the innermost place where a stable circle is possible. For a non-spinning black hole, the ISCO sits at 3 Schwarzschild radii, 3 times the radius of the horizon itself. If the horizon of a solar mass black hole is 3 kilometers across, then the ISCO is 9 kilometers out from the center, not far, and at that innermost stable orbit, matter is already moving at a large fraction of the speed of light. The geometry has become extreme enough that only near light speed motion keeps an object in orbit without falling in. For a spinning black hole, the situation is different and in some ways even stranger. The spin of the hole and the direction of the orbit interact. Prograde orbits, those that go around the hole in the same direction as the spin, can be stable much closer in. The ISCO shrinks. For a maximally spinning black hole, prograde matter can orbit in a stable circle almost at the horizon itself, racing around at a speed that approaches the speed of light. The inner edge of the accessible orbiting region is pulled down almost to the event horizon, nearly touching it. Retrograde orbits, those going against the spin, must stay farther out. Their ISCO is wider. Spinning and non-spinning, prograde and retrograde, the ISCO tells you where the last safe orbit lives. This matters enormously for what you actually see near a black hole, because just outside the ISCO, accumulating matter tends to pile up and orbit. Gas falling toward a black hole does not fall in cleanly and directly. It has some angular momentum, some sideways motion, and it tends to settle into a disk, the accretion disk, a vast flat swirl of gas and dust and plasma orbiting the black hole, spreading from far out inward toward the ISCO. As gas moves through the disk, spiraling slowly inward, it loses energy through friction and turbulence. That energy has to go somewhere. It goes into heat. The inner edge of the accretion disk near the ISCO reaches temperatures of millions of degrees, not surface temperatures like the Sun, which manages about 6,000 degrees at its photosphere. Millions. The gas in this region glows not in visible light, but in X-rays, high-energy radiation that carries the fingerprint of matter at extreme temperatures, being pulled apart and churned at the edge of something vast and dark. Looked at in X-ray wavelengths, the inner edge of an accretion disk blazes. It is some of the hottest, most energetically dense matter in the observable universe, a ring of fire circling the darkness. And this ring of fire is fantastically efficient. Efficiency in physics means how much of the input energy you actually get out as usable output, rather than losing it to heat or sound or some other waste form. Nuclear fusion, the process that powers the Sun and all the stars, converts less than 1% of the mass it processes into energy. It is the most powerful energy source we know how to use on Earth, and it manages under 1%. A non-spinning black hole's accretion disk falling matter, traveling inward to the ISCO and releasing its gravitational energy as it goes, can convert roughly 6% of the rest mass of infalling material into energy. 6 times better than fusion. Already astonishing. A maximally spinning black hole does better still. Because the ISCO sits so close to the horizon for a maximally spinning hole, infalling matter gives up far more gravitational energy before it crosses in. The efficiency can reach somewhere around 42%. Nearly half the mass of everything falling into a maximally spinning black hole can be radiated away as energy before that matter even crosses the edge. Black holes are the most efficient engines known in nature. The edge is surrounded by the most efficient fire in the universe. Astronomers use this efficiency to measure something they cannot see directly: the spin of the black hole. Watch where the accretion disk's glow cuts off. The inner edge of the disk marks the ISCO, and the ISCO's location depends on the spin. A non-spinning hole has its disk edge at 3 Schwarzschild radii. A maximally spinning hole has it almost at the horizon. Measure the radius of the disk's inner edge inferred from the temperature profile and the spectrum of the X-ray glow, and you can calculate the spin. We read the invisible rotation of a black hole's edge from the position of the fire around it. The edge tells its own secrets through the light of what it is consuming. Now, let us imagine you are no longer watching from outside. Let us imagine, very gently and without alarm, that you are falling in. You are far enough from a supermassive black hole that tidal forces are not yet lethal. You have crossed the region of the accretion disk, somehow navigated past the fire and the radiation, and you are on a free trajectory inward, falling freely as if in zero gravity. No thrust, no engines, just falling. And as you fall, the universe in front of you begins to change. The first thing you notice, already apparent long before the horizon, is that the sky ahead of you is not behaving normally. Light from distant stars and galaxies traveling toward you from every direction is being bent by the black hole's gravity. Photons that would have missed you are being curved around the black hole and redirected toward you. The stars in the forward direction appear compressed together, squeezed toward a point. The entire sky in front of you is being folded, collapsed, as if someone were pulling the universe into a smaller and smaller circle ahead. Stars that should be behind you, off to the sides, are bent by gravity and appear in front of you. The circle of the visible universe shrinks. The cosmos compresses itself into a shrinking, brilliant porthole of light directly ahead. This is called relativistic aberration. It is partly the effect of your speed, moving very fast toward the black hole, but it is also the extreme gravitational lensing, the bending of all incoming light, concentrating it forward. As you fall faster and approach the horizon, this effect becomes more and more extreme. The universe, the entirety of all visible stars and galaxies, and the faint glow of the cosmic microwave background concentrates itself into a smaller and smaller circle of light in front of you. Around it, darkness grows, the sky behind you empties, the void expands. All of existence squeezes into a single bright disk directly ahead. And that light is not simply compressed spatially, it is also energetically compressed. The light arriving from the universe ahead of you is blue-shifted. Your motion toward the light sources and the gravitational potential you are falling through both shift the frequencies of incoming photons upward toward higher energies. Visible light shifts toward the blue and then beyond it, toward ultraviolet and X-ray. The universe ahead of you brightens and changes color. The clocks of the cosmos, seen through that compressed circle of light, tick faster and faster relative to yours. You are receiving in real time the future of the outside universe delivered to your eyes at an accelerating rate. There is a beautiful and widely repeated claim that goes further than this. It says that as you fall into a black hole, you would see the entire future history of the outside universe play out before your eyes. The universe's story from now until its end, compressed into the moments of your infall. It is a vivid image. It is also important to be careful with it. In the idealized mathematical case of an eternal non-rotating black hole, the simplest solution, the amount of external history you see as you fall in, is actually finite. You do not see infinitely far into the future. You see some portion of the future compressed into a blaze of high-energy light, but not all of it, and not forever. The truly infinite future-seeing is associated with more exotic cases and more idealized geometries. In honest terms, what you would see is extraordinary enough without exaggeration. The universe's visible history, compressed and blue-shifted, playing out faster and faster in that shrinking circle of light, is already one of the most astonishing images physics permits us to form. hold it as the approximately true wonder that it is, rather than the infinite drama it sometimes becomes in popular telling. Meanwhile, as the forward sky compresses, the darkness behind you grows and begins to do something unexpected. The black hole's dark disk, which was a circle of absence in whatever direction you were originally falling from, grows. It fills more of your sky, and as you approach the horizon, extreme light bending pulls light from directions that should be behind you, curves it, and redirects it so that it appears to come from slightly in front of you. The darkness wraps around. The shadow of the black hole's edge expands past half your sky. By the time you are near the horizon itself, the dark disk of the black hole has swallowed more than half your visual field. The bright compressed universe has shrunk to a small circle directly ahead, and the darkness of the edge fills everything else around it. This is the view, a small, brilliant universe ahead, a vast encircling darkness around you, and you falling freely, feeling no weight, feeling no special sensation, just falling into an increasingly strange and concentrated sky. For a small black hole, a stellar mass one of a few suns, the journey would not continue gently for long, because tidal forces would already be significant. Tidal forces are simply the difference in gravitational pull across your own body. Gravity is stronger at your feet than at your head if you are falling feet first toward the black hole. That difference, that gradient, stretches you along the direction of fall. At the same time, gravity's lines of force converge toward the center, squeezing you inward from the sides. The combined effect is that you are stretched lengthwise and compressed sideways simultaneously. This is called spaghettification. The name is somewhat whimsical for a process that would be extraordinarily unpleasant. For a small black hole, these tidal forces become lethal while you are still outside the horizon. The tidal gradient across a human-scale object reaches the point where no body can remain intact. You are pulled apart, stretched into a filament before you even reach the edge. For a supermassive black hole, this is not the case. The tidal gradient at the horizon of a hole of millions or billions of solar masses is gentler, precisely because the gradient across any reasonably sized object is small compared to the overall curvature. You would cross the event horizon of a supermassive black hole completely intact. The edge would be silent and unmarked. Your body would feel nothing locally. Spaghettification would still happen, eventually, as you fell deeper and the curvature increased, but it would happen somewhere inside the horizon, well after you had crossed it. Bigger black holes are gentler at their edges. The most extreme objects in the universe have the most peaceable boundaries. And so there you are inside, you have crossed. The horizon is behind you now, though you could not point to it. It has no marker. It is simply a boundary in space-time that you passed, and the universe continues to look, for a brief moment, recognizably like the universe. Ahead, that compressed bright circle still glows. The darkness is vast around you. And then there is the question of what you can do. The answer is, you can move in most directions, but not all of them. Inside the horizon, the inward direction toward the center has become time-like. It is not simply a direction in space that leads somewhere you could choose not to go. It is, in the geometric language of general relativity, more like the future than like a place. You can no more avoid moving toward the center than you can avoid tomorrow. Every path through space-time inside the horizon, no matter which way you point yourself, curves inward. Not because of a force you can resist, but because inward has become the direction of increasing time, and time only goes one way. This leads to a strange conclusion about struggle. If you are inside the horizon and you fire your engines to try to escape outward, you do not succeed, but you do use fuel, and burning that fuel changes your trajectory. In the idealized physics, firing toward the center would delay your arrival at the singularity, but trying to accelerate outward, to fight the geometry, to push against the direction of time, actually moves you along certain trajectories that reach the singularity sooner. The harder you struggle to escape in some configurations, the faster you arrive at the place where the equations break down. The most efficient strategy for extending your survival inside the horizon is to do nothing, to simply fall freely, to not struggle, to move along the natural geodesic, to fall with the same unhurried passivity with which the light falls, with which time itself progresses. The maximum time you have between crossing and reaching the singularity depends on the mass of the black hole. For Sagittarius A, the supermassive black hole at the center of our own galaxy, calculations suggest the available time would be on the order of seconds to tens of seconds of experienced time between crossing the horizon and reaching the center. For a much larger hole, one of a billion solar masses, the survival time might extend to minutes. More than that is not a comfortable gift. It is a very finite pocket of continued experience inside an unreachable interior. You would spend it watching the compressed universe ahead, aware that the center is your future and that no engine can change that, and eventually tidal forces would make themselves known. The edge of the largest black holes is generous and gentle. What lies beyond it is not. But you are not inside one. You are here in the quiet, letting these ideas settle gently into sleep. The infalling view, the sky squeezing to a circle, the darkness wrapping around, the forward blaze of compressed light, the stillness of free fall at the edge of something that has made itself a whole in the future. And these are real pictures that real physics permits. They are verified not by someone who went there, but by the equations that have passed every other test we have put to them, equations born from a wartime letter and confirmed by a century of light and clocks and laser-tracked satellites and gravitational waves arriving from merging holes a billion light-years away. Let the weight of that settle. And let the body settle too. The ergosphere, swept space, the Penrose process, the ring of fire at the ISCO, the sky compressing ahead, and the darkness wrapping behind. These are the neighborhood of the edge, not a wall, not a cliff, a geometry, a place where the meaning of words like inside and outside, future and direction, up and away, have shifted just enough that everything familiar becomes strange, without a single wall or warning sign to mark the shift. And the shift is quiet. That is what keeps returning. However dramatic the physics, the experience of the boundary, for an infaller at a supermassive black hole is quiet. A gradual change in the sky. A gentle tightening of the circle of light ahead. A darkness that grows, no alarm, no sensation of crossing, just the universe rearranging itself around you slowly and without apology into a new configuration where the future points in a direction it did not point before. Wherever you are right now, whatever corner of the planet holds you in its gravity tonight, you are falling freely in a sense too. Not toward a singularity, but through time, which is also a direction you cannot choose not to move in. The floor below you is a different gravitational potential from the ceiling above, and a clock there ticks in the same geometry, infinitesimally differently from a clock up here. You are made of quantum fields. You are threaded by neutrinos from the sun. You are held by a curvature in space-time that the Earth creates, which is a smaller version of the same mathematics, the same general relativity, that bends light into rings around a black hole 30 million kilometers across. The edge is 44,000 light-years from you in the case of Sagittarius A, if you want the nearest one. 26,000 light-years to be precise. Far enough that its darkness is no danger. Close enough that it is real. Close enough that in 2022, the Event Horizon Telescope resolved its shadow with radio waves threaded across a planet-sized network of dishes and confirmed that there is indeed a darkness at the heart of our galaxy, an edge of nothingness, an event horizon orbited by hot gas moving at a fraction of the speed of light, its inner edge marking the ESCO, its spin detectable from the asymmetry of the glow. We have seen it, not with the naked eye, not with a telescope you could hold, but with the planet itself turned into a lens. We have seen the silhouette of the edge. And that is not the end of the strangeness, there is more. The horizon glows in the mathematics, though we have never seen that glow. The horizon stores information, in the theory, on its surface. The horizon obeys laws that look exactly like thermodynamics, which is the physics of heat and entropy in steam engines, except the steam engine is a black hole and the heat is written into the geometry of the boundary. The horizon, when a black hole merges with another, rings like a bell, and we have heard that bell. There is still more to come in a little while. But not yet. For now, let the frame dragging slow the rotation of your thoughts. Let the ergosphere of your attention relax its forced orbit. Let the ISCO of your concentration ease outward from the center. You do not need to hold any of this tightly. These ideas will persist whether you grasp them or not. The geometry is not going anywhere. The edge is patient. It has been curving space-time for a long time already, and it will continue to do so long after this particular night has become another morning. Rest here for a moment, at the boundary between knowing and dreaming. The photons in the accretion disk are still circling, out there in the X-ray dark, heating to millions of degrees, spiraling in toward the ISCO, giving up their energy to the fire at the edge. The ergosphere is still sweeping space around the spinning hole. Frame dragging is still turning the geometry in slow, enormous circles around the event horizon. The ISCO marks the innermost safe path, and just inside it all stability ends, and there is only the long, quiet fall inward into a future that looks nothing like the one we know. And somewhere in the middle distance of your drowsing mind, perhaps an image holds. A small circle of light. The entire compressed universe, all the stars and galaxies and the faint warm glow of the beginning of time, squeezed into a single bright point ahead. Darkness wrapping around you from every other direction, and the feeling, unmistakable, that you have crossed something, and that the something left no mark, made no sound, offered no sign. That is the edge. That is what it is like. And the next part of the story is waiting on the other side of sleep. And now, quietly, we arrive at one of the strangest discoveries that has ever been made about the edge. Stephen Hawking in 1974 showed that black holes are not entirely black. They glow. The horizon itself radiates, faintly, almost impossibly faintly, but genuinely, with what we now call Hawking radiation. And this is a thing worth sitting with because it changes something fundamental about what the edge is. The mechanism is rooted in quantum physics, in the behavior of empty space itself. Even the void at the smallest scales is not truly empty. It seethes with what physicists call quantum fluctuations, pairs of particles and antiparticles that flicker into existence and annihilate each other almost instantly before the universe has time to object. Ordinarily, this happens everywhere and leaves no trace. But right at the edge of a black hole, something different occurs. A pair forms just at the horizon, and before the two can find each other again, the gravitational difference between the inside and the outside pulls them apart. One falls in, the other escapes, and because the infalling one carries, in a sense, negative energy into the hole, the black hole itself loses a tiny, vanishingly small amount of mass. The escaping particle streams outward as radiation. the horizon leaks. This is not an observation. Hawking radiation has never been directly detected, and for good reason. The glow is extraordinarily cold. The bigger the black hole, the colder it is. A black hole of 1 solar mass would radiate at a temperature of roughly 60 billionths of a single Kelvin. To put that in some kind of frame, the coldest temperature ever achieved in a laboratory is a few billionths of a Kelvin. The cosmic microwave background, the faint afterglow left over from the early universe bathing all of space, sits at about 2.7 Kelvin. A stellar mass black hole, by comparison, glows at a temperature 60 times colder than that background. It is not just cold, it is almost unimaginably cold. The edge of a black hole is among the coldest things the universe contains, measured by what it radiates. And this leads to a consequence so strange it takes a moment to fully land. Supermassive black holes, the giants, many millions or billions of times the mass of the Sun, are colder still. Their Hawking temperature is so low, so far below the temperature of the cosmic microwave background, that they actually absorb more radiation from the universe around them than they emit. They are not evaporating, they are, in a sense, still drinking. For those enormous black holes to begin truly evaporating, the universe itself would first have to cool below their Hawking temperature. And that will not happen for a span of time so vast it barely fits into language. Trillions upon trillions of years from now, long after the last stars have burned out, long after the cosmic background radiation has thinned and faded to near nothing, only then will the great supermassive black holes begin to slowly lose their edge. The situation is different for smaller black holes. A black hole the mass of the Moon, which would be fantastically tiny, just a fraction of a millimeter across at the horizon, would glow at roughly room temperature. Something you could hold your hand near and feel the warmth of if somehow you could survive being near it, which of course you could not. And something smaller still, a truly tiny black hole, would be hot. It would glow brightly. It would be losing mass quickly. The relationship between size and temperature for black holes is the inverse of what we'd expect from anything else. The smaller they get, the hotter they get, and the faster they evaporate. This means that evaporation is not a gentle, steady process. It accelerates. A black hole, losing mass, becomes smaller, and a smaller black hole is hotter, so it radiates faster, loses mass faster, becomes smaller faster, grows hotter faster, until at the very end, the process is not a slow fade, but a burst, a flash. The final moments of a black hole's evaporation, in theory, release an enormous pulse of energy. The edge does not go quietly, it ends in brightness. For a black hole formed from a star, the timescale for this to happen is staggering. A stellar mass black hole would take something on the order of 10 to the 67th years to fully evaporate. The current age of the universe is just under 14 billion years, which is less than 10 to the 11th years. So the universe as it now exists has consumed an almost negligible fraction of the time a stellar black hole would need before it begins to flash out. These objects, once formed, are effectively eternal on any scale we can meaningfully contemplate. But eternal is not the same as forever. The edge, given enough time and an empty enough universe, eventually vanishes. And this slow evaporation, this quiet leak from the horizon, is where one of the deepest puzzles in all of modern physics lives. The information paradox. When something falls into a black hole, it carries information, the precise quantum state of every particle, every configuration, every detail. Quantum mechanics is insistent that this information cannot be destroyed, that it must be preserved somewhere, that the universe keeps its books. But when a black hole evaporates, what it emits, Hawking radiation in its simplest form, is thermal, random, It carries no record of what went in. If you watched a library fall into a black hole and then caught all the Hawking radiation as the hole slowly evaporated, you would find nothing that could tell you anything about those books. The information appears to be gone. This troubles physicists deeply, not just as a matter of aesthetics, but as a matter of principle. If information can be destroyed, something at the foundations of quantum mechanics breaks. Whether information is somehow preserved, encoded in subtle correlations in the Hawking radiation, imprinted on the horizon and released over time, or rescued by some mechanism we do not yet understand, remains an open question. One of the most important open questions in physics centered entirely on the behavior of the edge. And the edge is strange not just in what it does to information, but in what it conceals, because at the center of every black hole, general relativity predicts something it cannot describe, a singularity. At the core, the density becomes infinite, the curvature of space-time becomes infinite, the equations produce answers that are not answers. They produce infinities that mean the theory has reached its own boundary, the edge of its own explanatory power. The singularity is not a place in the ordinary sense, it is a breakdown. It is where the map runs out. For a non-spinning black hole, the Schwarzschild solution, the singularity is a point. For a spinning black hole, described by the Kerr solution, named for Roy Kerr, who found it in 1963, the singularity takes a different shape. It is a ring, not a point, but a circle, threaded through the interior of the spinning hole. And in the idealized mathematics of the Kerr solution, certain paths through the interior seem to pass through the ring without hitting it and continue into regions of space-time that look, on paper, like other places entirely, other copies of space-time connected through the ring. There is even an inner horizon inside the outer one, a second boundary in the spinning case. But this is where honesty about the physics becomes important. Those inner regions, those seemingly passable ring singularities, those other space-time connections, they exist in the idealized, perfect Kerr solution for a spinning black hole in an otherwise empty universe. Real black holes are not perfect. They are surrounded by infalling matter and radiation. Physicists believe, and there are strong arguments for this, that the inner horizon is unstable, that any real infalling matter would destabilize it, that the exotic interior geometry of the Kerr solution would not survive contact with the messy reality of actual black hole physics. The ring singularity and its apparent trapdoors are, almost certainly, artifacts of an idealized equation applied beyond its range of validity rather than passable features of actual black holes. They are a hint, perhaps, of something deeper, but not a confirmed doorway. The mathematics points somewhere. Whether reality follows is another matter. What does seem likely, what is enshrined in what Roger Penrose called cosmic censorship, is that singularities are always hidden, always wrapped inside a horizon. You cannot, from outside, observe a singularity directly. The edge exists, in part, to keep the place where physics breaks down out of sight. The universe, perhaps mercifully, draws a curtain. Whether cosmic censorship is always enforced, whether there are circumstances that could produce a naked singularity visible to the outside world, remains a subject of ongoing investigation. But the conjecture holds in every case that has been carefully studied. There is one more thing about the horizon that remains debated, and it touches directly on the experience of crossing it. We have spent a great deal of time with the picture of a gentle, unmarked edge, an infaller who feels nothing, whose local experience gives no warning. This comes from the equivalence principle, one of the deep postulates of Einstein's general relativity, that the experience of falling freely in a gravitational field is locally identical to floating in empty space. Nothing local distinguishes free fall, so nothing at the horizon, which is a surface you cross in free fall, should feel any different from empty space. But some physicists have proposed that this picture is wrong, that the requirements of quantum mechanics and the requirements of consistency for the Hawking radiation actually force the horizon to be violent. This is the firewall proposal put forward by Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully in 2012. Their argument is that in order to preserve the information carried by infalling matter, the Hawking radiation escaping the hole must be entangled with that infalling matter in a particular way, and that this entanglement, to be consistent with quantum mechanics, would require the state at the horizon to be what amounts to a wall of extremely high-energy radiation. A firewall. Something an infaller would hit with catastrophic force, not drift through with calm serenity. The firewall, if real, would violate the equivalence principle directly. It would mean Einstein was wrong in his most cherished postulate about gravity and acceleration, that the horizon is not locally empty, that the edge is violent after all. This is the tension at the heart of the debate. Preserving quantum mechanics seems to require violating general relativity at the horizon, and preserving general relativity seems to require throwing away something about quantum information. The resolution, if there is one, is not yet known. The edge holds this tension without resolving it patiently, while physicists argue, and the universe continues to keep its own counsel. Let us pause here in this space of open questions and turn for a moment to scale, because part of what makes the edge so remarkable is the sheer range of it, the variety of sizes and masses at which these horizons exist. The largest confirmed black hole we have discovered is one called photon 618. Its mass is somewhere around 66 billion times the mass of the Sun, and its horizon, its event horizon, the edge, would span a distance roughly 12 times the diameter of our solar system. Light, traveling at the speed at which light travels, would take on the order of days just to cross from one side of that horizon to the other. If you replace the Sun at the center of our solar system with photon 618, its edge would swallow everything, every planet, every asteroid, every comet, and extend far beyond. A horizon so vast you could spend a human lifetime falling through it. Closer to home, much closer, is Sagittarius A Had, the black hole at the center of our own Milky Way. It weighs about 4 million solar masses. Its event horizon is roughly 24 million kilometers across, 17 times the width of the Sun, but still small enough that it would fit inside the orbit of Mercury, the innermost planet. 26,000 light-years from where you are lying right now, there is an edge of darkness in the center of this galaxy, and it is, by the standards of black holes, a modest thing, city-sized in a way, though the city would span millions of kilometers. Then there is M87 ticks at the black hole at the center of the galaxy Messier 87. It weighs about 6.5 billion solar masses. Its horizon is so large that the entire orbit of Pluto, which traces a path billions of kilometers from the Sun, would fit inside it many times over. Its shadow did the horizon itself, but the shadow cast by the bending of light, which is larger than the horizon, spans roughly the size of our solar system. M87 sits 55 million light-years away, and yet we have seen it. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. That image, under a blurry, glowing ring of orange and red around a region of darkness, was M87. The telescope that made it was not a single instrument. It was an array of radio observatories spread across the Earth, coordinated with extraordinary precision, together forming a virtual telescope the size of the entire planet. The angular resolution required to resolve that shadow at that distance is something like seeing a single coin on the surface of the Moon. The whole Earth, working together, could just barely do it. And then in 2022, the same collaboration turned its attention to Sagittarius A, our own galactic center. closer and therefore spanning a larger angle on the sky, but harder to image because a black hole that massive is still much smaller than M87 star, and the material around it swirls and shifts on human timescales. The gas turbulence near Sagittarius A changes in hours, while the exposure needed to capture the image takes much longer, requiring painstaking computational work to reconstruct a coherent picture from the noise. But they managed it. There, at the heart of the Milky Way, another bright ring of light around another region of darkness, another edge made visible 26,000 light-years away. It is worth saying clearly what those images show and what they do not. The dark region at the center of those images is not the horizon itself. It is what's called the black hole shadow, the region of the sky from which no light reaches us, partly because of the horizon and partly because of the extreme bending of light in the horizon's neighborhood. The horizon itself is smaller. Gravity magnifies the darkness, stretching it outward so that it appears to us about 2.5 times larger than the horizon alone. We have never seen the edge directly. We have seen the silhouette it casts on the universe behind it, enlarged and curved by its own gravity. It is as if you could not see a man standing in a spotlight, but you could see the enormous shadow he threw onto the wall, a shadow larger than the man himself. That is what we have seen. Now, something that might seem puzzling. We have been describing black holes as objects that grow, that absorb matter, that merge with each other, that increase in mass. And yet we also described a little while ago how infalling matter never actually reaches the horizon in the time of a distant observer. It slows, it freezes, it fades to red. So how does anything ever get in? How does a black hole grow? The resolution is one of those places where language and intuition need a little help from the mathematics. The picture of matter freezing at the horizon is the picture as seen by a distant, outside observer, described in the coordinate time of someone watching from far away. In that frame, infalling objects do asymptotically approach the horizon without crossing it. But the black hole is also feeding on the energy of all that infalling matter, even before it formally crosses. The gravitational redshift carries energy in, the mass of the system increases, and the horizon expands to encompass it. The horizon moves outward to meet the infalling matter before the matter crosses in coordinate time. They meet. The horizon grows. This is what the old name captured so well, frozen star. The name used before John Wheeler popularized the term black hole around in 1967. A frozen star is precisely what a collapsing object looks like from outside, a star that seems to slow its collapse and freeze at the boundary, its light red-shifting and dimming toward invisibility, hanging there forever on the edge. And a grown black hole, eating gas from an accretion disk, is simply more of the same. The material piles up arbitrarily close to the horizon, so close it is effectively inside, and the horizon expands to include it. The frozen star and the grown black hole are the same object, seen from outside, expressed in two compatible languages. The crossing happens, the geometry ensures the horizon accommodates it. The outside observer sees the long, slow redshift instead. And on the subject of silence, of what the edge announces, nothing, absolutely nothing. If you fell into a large enough black hole, one of the supermassive giants, millions or billions of solar masses, you would cross the event horizon in complete and unremarkable silence. No siren would go off, no light would change, no force would push or pull you differently than a moment before. The equivalence principle, setting aside the firewall debate for a moment, says the local experience of freefall cannot be distinguished from floating in empty space. You would feel weightless, drifting the way you feel in any free fall. You would notice things changing, certainly, the sky ahead of you compressing, the universe's light gathering into a shrinking, brilliant circle in front of you, the darkness expanding from behind until it swallows everything except that single luminous point. But the crossing itself, the crossing of the horizon, would leave no mark. There is nothing there to mark. The horizon is a mathematical boundary, a global feature of the space-time, a place defined not by what exists there, but by what the future holds, by the fact that no path from inside leads to infinity. You cannot feel your own causal future narrowing. By the time you wondered whether you had crossed, you would have crossed. Long ago, perhaps. And the wondering would change nothing. The universe you left would be behind you, but behind you in a direction that is no longer a direction. Behind you in a direction that is now the past and unreachable, not because it is far away, but because it is backward in time. The horizon announces itself only in hindsight, and by then the announcement is irrelevant. And this is, quietly, one of the most extraordinary things about the edge. Not the violence of it, not the drama, but the silence. The absolute, unmarked, unremarkable silence of crossing the most significant boundary in the universe. You would not know, you would just fall, and keep falling. There is a strange gentleness to that. For the largest black holes, the edge is mostly empty. A region of curved space-time with nothing remarkable locally, no fire, no wall, no sign. A boundary written only in the structure of what comes next, in the narrowing of all possible futures toward a single point. The most extreme object in the universe at its edge is indistinguishable from open space. And yet, so much is written there. The Bekenstein-Hawking entropy, named for Stephen Hawking and Jacob Bekenstein, who worked in the early 1970s to understand what thermodynamics means for a black hole's horizon. Bekenstein noticed in 1972 that the area of the event horizon could never decrease in classical physics, just as entropy in thermodynamics can never decrease, and proposed that the horizon area was proportional to entropy. Hawking was initially skeptical, but his own discovery of Hawking radiation in 1974 confirmed it. The horizon has a real physical temperature and a real physical entropy proportional to its area. The edge is not just a boundary, it is, in a sense, a thermodynamic object. It has temperature, it has entropy, it obeys laws, and the amount of entropy is staggering. For a black hole of even one solar mass, the entropy of the horizon, the number of microscopic configurations consistent with that horizon, is so vast that writing out the number would require on the order of 10 to the 77th digits. A number with 77 zeros behind it just to write the exponent, and then that many zeros for the number itself. This exceeds by an enormous margin the entropy of the Sun, of the galaxy, of all the stars in the observable universe combined. A black hole is the most entropic object that can exist for its size. The edge is the most information-dense surface in nature. And this is where the holographic principle enters, quietly and surprisingly. The entropy of a black hole is proportional not to its volume but to the area of its horizon. In ordinary physics, the information content of a system scales with its volume. More space, more stuff, more information. But for a black hole, everything is captured by the surface. The three-dimensional interior is fully encoded on the two-dimensional edge. This is the seed of the holographic principle, the conjecture now supported by rigorous work in string theory and quantum gravity, that any region of space and everything inside it can be fully described by information living on the boundary of that region, the way a hologram encodes a three-dimensional image on a flat surface. The horizon may be the universe's most perfect hologram. Everything that ever fell in, every star, every gas cloud, every photon, every person, everything, might be encoded on the edge. Not lost, not destroyed. Written there in some language we do not yet know how to read. The area theorem, Hawking's area theorem, says the area of the horizon can never decrease in classical physics. If you drop something in, the area grows. If two black holes merge, the combined area of the new horizon is at least the sum of the areas of the two that joined. This was beautifully confirmed in a sense by the detection made in September 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. Two black holes, one about 36 solar masses and one about 29 solar masses, spiraled toward each other across a distance of roughly 1.3 billion light-years and merged in a fraction of a second. The energy released in that merger, carried away, as ripples in space-time itself, as gravitational waves, was equivalent to roughly 3 times the mass of the Sun, converted entirely into energy in an instant. And the new horizon that formed was larger than the sum of the original two. The area theorem held. The edge kept its promise. What LIGO detected was a brief, rising chirp in the fabric of space-time, a wave that compressed and stretched the distance between the instrument's mirrors by a fraction of the diameter of a proton. Across 1.3 billion years of traveling, a ripple from two black holes touching. And embedded in that signal was something called the ring down. After the merger, the new, combined black hole was not yet settled. It was vibrating, wobbling, its horizon distorted from a perfect sphere into something more irregular. And as it settled, it radiated, not light, not matter, but gravitational waves at a specific frequency determined entirely by its mass and spin. Like a bell struck and then allowed to ring out. The tone of that ring, captured in the data, told physicists exactly what had formed the mass, the spin, the character of the new edge. We did not see it, we heard it. We read the edge from its dying note. And now, one more thought about the edge before we begin to let it go. There is a question embedded in everything we have visited tonight. A question that each strange fact orbits without quite landing on. What is the horizon, really? Not in the mathematical description that we have, but in some deeper sense, in whatever sense physics reaches for when it runs out of equations. Some physicists think the horizon is purely relational, a boundary defined by the future of the space-time with no local existence at all. It is not a thing, it is a condition. Others think the Bekenstein-Hawking entropy points to something real, something written in the microstructure of space-time at the edge, degrees of freedom living there in quantum gravity we do not yet understand. Others again think the holographic principle means the horizon is, in some sense, more fundamental than the interior it bounds, that the edge is not a consequence of the black hole but something closer to its definition. And some think the firewall, the violent edge, means all our gentle pictures need rethinking. The no-hair theorem tells us that the edge is, in one sense, the simplest thing in nature. Mass, spin, charge. 3 numbers and you have fully described the edge of a black hole, no matter what fell in to make it. 2 black holes with the same mass and spin and charge are not just similar, they are identical, indistinguishable. The edge erases everything else. It does not remember whether it was built from the collapse of a star or the slow accumulation of gas, or, in principle, an infinite quantity of grand pianos falling in one after another. The edge forgets. It holds only the barest outline of what made it. In practice, real black holes carry almost no charge. Charge would quickly be neutralized by the surrounding plasma. So in practice, just 2 numbers define an edge, mass and spin. The most complex gravitational objects in the universe, the heirs of everything that ever crossed their boundaries, fully described by 2 quantities, the simplest imaginable description, an extreme object and an extremely simple one simultaneously. Hold that thought. Hold it gently. The simplest and the most extreme, the most entropic and the most minimal. The edge that forgets everything and possibly remembers everything on its surface. The boundary you cannot feel and yet cannot return from. The place where time becomes a direction in space. The place where light orbits. The place where the entire sky compresses to a single circle of brightness and then is gone. Take a breath. Let the edge be what it is, strange and simple and vast and small and cold and, in certain lights, possibly glowing very faintly with the most distant warmth. We have come a long way tonight, across the horizon and back, around the photon sphere and through the ergosphere, down to the ISCO and up to the ring-down tone of two black holes meeting 1 billion years ago. We have visited the place where time stops from outside and where it continues perfectly normally from inside. We have seen the shadow of M87 cast by gravity 55 million light-years away, and the shadow of Sagittarius A in the heart of our own galaxy. We have held for a while the paradox of information at the edge, the thermodynamics of the horizon, the entropy written in area, the hologram that may contain everything. And maybe some of it has drifted past you, half heard, becoming part of the background texture of sleep. That is fine. That was always fine. These ideas do not require full attention to leave something behind. They will settle. The photon sphere will still be there in the morning. The area theorem will still hold. The no-hair theorem will still have forgotten your piano. But here is the thing, the last thing, that feels worth staying awake for just a moment longer to say. You are made of this. Not metaphorically, not as a figure of speech. The atoms in your body were forged in stellar cores and scattered by stellar explosions, explosions that left behind the dense remnants from which black holes form. The very curves in space-time that we have been exploring tonight are active everywhere, not only near black holes. The Earth curves space-time slightly and your clock runs faster by about 38 microseconds per day than a clock in orbit would. This is why GPS satellites have to correct for general relativity, or they would drift off by kilometers within a day. The curvature of space-time that reaches its most extreme expression at the edge of a black hole is the same curvature that keeps you from floating off the surface of the Earth right now. The physics is not elsewhere. It is here. It is in the gentle weight of the blanket on your chest, in the slow revolution of the planet under you, in every photon of the lamp still burning in the corner of the room. The horizon of a black hole is where all of this becomes extreme, naked, exposed, where time and space trade places, where light orbits and then escapes or doesn't, where entropy reaches its theoretical maximum, where the equations we use to describe the universe push through to their limits and then pass them into silence. But the same laws, the same geometry, the same exquisitely tuned and interconnected physics. That is here too. In the dark, in the quiet, in you. You are a local region of curved space-time that has, for a while, developed the capacity to wonder about its own curvature. That is what you are, and what you have been doing tonight, lying there in the dark, is the universe bending back on itself to look at one of its own edges. That seems like a good thing to carry into sleep. We have been to the edge and back. We have crossed it, in imagination, with the calm that a large enough black hole would offer. No drama, no wall, just a mathematical line in empty space and everything changed. We have hovered at its threshold and felt the near infinite thrust required to stay still. We have watched time slow and light grow red, and the frozen images of infalling things accumulate at the boundary, dimming forever without quite disappearing. We have orbited with the photons at 1.5 Schwarzschild radii, knife edge balanced between escape and capture. We have been flung around the ergosphere, allowed to leave, extracted a little energy from the spinning hole's rotation on the way out. We have stood at the ISCO and felt the last stable orbit, and then let go and fallen. We have not come back, technically. But then the story never needed us to. The horizon is patient. It has been curving space-time since long before anyone thought to name it. It will keep curving space-time long after every name has been forgotten. Wherever you are listening from tonight, in whatever corner of the world, in whatever quiet room or train car or pool of lamplight, I hope there is something soft nearby. I hope the night outside is doing whatever night does, where you are, whether it is cold or warm, rainy or dry, whether the window shows stars or clouds or the pale wash of a city. All of those places, all of those skies are threaded through with the same space-time that curves so dramatically at the edge of a black hole. You are right now in the same universe as Sagittarius A and M87s and TON 618. The same physical laws reach from you to their horizons without interruption. That is a long way for a thought to travel at the end of a night. If you enjoyed this slow journey through the edge, if some of it settled gently, if you woke with even one image that stayed, the orbiting light, the frozen figure at the horizon, the bell tone of two black holes meeting, a like and subscribe helps this channel more than you might expect. Small creators like me rely on your support to keep making these slow, careful nights. And if you feel like it, tell me, where are you listening from and what time is it in your corner of the world? I love knowing where these words land. Until next time, stay as long as you like in Nightoria. Good night.